Welcome students, we are learning aldehydes, ketones and carboxylic acids, and in this second video lecture you will be learning preparation of aldehydes. In the previous video we learned the functional group of aldehydes, ketones and carboxylic acids. Let us begin our session. First method of preparation of aldehyde is oxidation of primary alcohol. Primary alcohol means the OH group attached to that carbon atom which is further attached to one carbon atom or no carbon atoms. So here we have a primary alcohol RCH2OH. When this is treated with pyridinium chlorochromate or pyridinium dichromate, the process is oxidation. It means it is either the addition of oxygen or the removal of hydrogen atom. So in this case it is a removal of hydrogen atom. So that is going to remove the water molecule, two hydrogen atoms from primary alcohol, and the oxygen atom or the nascent oxygen atom which is to be removed in the form of water leads to the formation of RC double bond OH, which is a general form of aldehyde. Wherever we take R group, it becomes a general reaction. So PCC and PDC are pyridinium chlorochromate, pyridinium dichromate, which are going to act as catalysts. We learn this with examples. First one, CH3 CH2 CH2OH. The OH group attached to the carbon which is further attached to only one carbon atom. So it is again a primary alcohol, and the name of the alcohol is propane 1-ol or 1-propanol, which undergoes oxidation in presence of PCC or PDC, removal of two hydrogen atoms, and that forms aldehyde. CH3 CH2 CHO, again 3 carbon atoms, propanol. One more example. Here benzyl alcohol, it is a phenyl group to which CH2OH group is attached. OH group attached to the carbon atom which is further attached to only one carbon atom of phenyl group, which undergoes oxidation in presence of PCC or PDC, removal of two hydrogen atoms along with oxygen, water is removed, it forms benzaldehyde. Moving further, the second method of preparation of aldehyde is by catalytic dehydrogenation of primary alcohols. Dehydrogenation means removal of H2 gas, that is in presence of a metal catalyst. RCH2OH, again a primary alcohol which is treated with copper 573 Kelvin. So copper is a catalyst, it is a metal catalyst which is going to remove two hydrogen atoms from primary alcohol, leads to the formation of RC double bond OH. It is removal of hydrogen gas, hence it is catalytic dehydrogenation. We learn the example. It is a 6-membered alicyclic compound, it is not a benzene, cyclohexyl methyl alcohol, which is treated with copper at 573 Kelvin temperature, removes two hydrogen atoms and forms cyclohexane carbaldehyde. Moving to the third one, from hydrocarbons, ozonolysis of alkene. Ozonolysis means addition of ozone or O3 to alkene. So breaking of bonds by ozone is called ozonolysis, or addition of ozone is ozonolysis. So we have a alkene, it is ethene, which is treated with ozone in presence of carbon tetrachloride. There is a formation of ozonoid. So this double bond is going to change the picture to CH2 groups as it is, and we are adding 3 oxygen atoms, and they are linked to carbon atoms in this manner. So it is 5-membered cyclic compound is formed. It is an adduct. It is ozonoid. This ozonoid is treated with zinc in presence of water. Bond breaking leads to the formation of respective aldehyde. In this case, the groups attached to double bond are same, CH2, CH2, hence the product formed is also the same. In other words, you can understand this as, in presence of zinc, water, these electrons are transferred to carbon oxygen bond, it becomes a double bond, and here the bond breaking takes place. These electrons are transferred to carbon oxygen, this bond also breaks, as there is a formation of total 4 bonds, carbon 1 2 3 4, here also carbon 1 2 3 4, because this is going to form double bond. So these electrons are transferred to the oxygen atom, leading to the formation of respective aldehyde. Another example for ozonolysis process. Now we have taken CH3 one side, CH3H another side. The 2 carbon atoms which are bonded with a double bond, they contain different groups. Hence, we can expect 2 different carbonyl compounds. One is CH3 C double bond O CH3, ketone is formed, and the other one is CH3 C double bond O H, aldehyde is formed. So one side is going to form ketone, another side is going to form aldehyde. So the name of the compound is 2-methyl-2-butene or 2-methyl-butene, which undergoes ozonolysis in presence of carbon tetrachloride. Ozonoid is going to be formed. So again there is a formation of 5-membered cyclic compound. So after the addition of zinc in presence of water, breaking of bonds takes place, leading to the formation of ketone and aldehyde. So as we are learning the preparation of aldehyde, we can concentrate on the second product, acetaldehyde. Moving further, fourth process of preparation of aldehyde, that is hydration of alkyne. Hydration means addition of water. Alkyne, it is triple bonded hydrocarbon. So we have acetylene or ethine, CH triple bond CH, which is treated with water in presence of 40% of H2SO4 and 1% of HgSO4. So water is written in this form, HOH. You can write H2O also. So we are adding hydrogen and hydroxyl groups to alkyne. You can concentrate on this product. So CH triple bond CH. Now it becomes a double bond, as one of the hydrogen atom is added to first carbon atom. You can see here CH2 it becomes. Then the second OH group is going to attack to another adjacent CH. Hence there is a formation of OH. This undergoes the formation of enol. En means double bond, all means OH group. Enol formation takes place, and which undergoes tautomerization, as this is an unstable compound. Tautomerization leads to interchange the hydrogen atom position from OH group to CH2. So it transfer to CH2, leads to the formation of CH3. Instead of double bond, now it is single bond, and new bond is formed between carbon atom and oxygen atom. The valency of first carbon atom remain as it is, which is going to form one bond with CH3, another with hydrogen, 2 with oxygen. So all 4 valencies are satisfied. So like this we can prepare aldehyde by hydration of alkynes. Moving to the next one, reduction of acyl chlorides. Acyl chlorides are the derivatives of carboxylic acids. RCOOH is converted into RCOCl by replacing OH of carboxylic acid by halogen atom. So this compound is acyl chloride. So reduction is removal of oxygen or addition of hydrogen. This acyl chloride undergoes the addition of hydrogen in presence of PDBaSO4, sulfur or quinoline. So this catalyst which we are adding is known as Lindlar catalyst, one of the most important catalyst used for the reduction process. So we have COCl which can be converted into CHO. This is the work of this Lindlar catalyst. Addition of hydrogen in presence of Lindlar catalyst, COCl is converted into CHO. So in this process, the bond between carbon and chlorine breaks and this H2 is going to add in this fashion, which leads to the formation of HCl as a byproduct, and along with that RC double bond OH aldehyde is formed. The whole reaction is known as Rosenman reaction, and with the help of this reaction we can prepare only aldehydes. Ketones cannot be prepared because we are adding hydrogen atom in place of Cl. Hence we can prepare only aldehydes, not ketones. Moving further, example CH3 C double bond OCl. We can take any alkyl or aryl group in this CH3 place. Name of the compound is acetyl chloride, which undergoes the addition of hydrogen in presence of Lindlar catalyst, that is PD in presence of BaSO4, sulfur or quinoline. The product is going to form by breaking carbon-chlorine bond and the addition of hydrogen on either side. So that leads to the formation of HCl as byproduct and CH3COH. Acetaldehyde is going to be formed. Next process, reductive hydrolysis of nitriles or cyanides, RC triple bond N, alkyl cyanide or alkyl nitriles. This alkyl cyanide undergoes the reaction with stannous chloride in presence of HCl, which is going to form aldehyde as a product. But the reaction between SnCl2 and HCl you can understand like this. SnCl2 that react with HCl to form SnCl4, the either side of triple bond, leads to the formation of CH double bond NH dot HCl. This RCH double bond NH is known as imine. Now this imine undergoes hydrolysis, that is addition of water. From water, oxygen is added to CH side and H2 is added to NH side. So that leads to the formation of RCHO and NH3 dot HCl or NH4Cl. So you can see the product here. First one RCHO and second one NH4Cl, and this whole reaction is known as Stephan reduction. We learned Rosenman reaction and now it is Stephan reduction. Rosenman reduction, it is in presence of Lindlar catalyst, hydrogen in presence of palladium and BaSO4, sulfur in presence of quinoline. And in Stephan's reduction we are using the catalyst SnCl2 and HCl combination. So the work of SnCl2 HCl is to convert cyanides into aldehydes. And remember dear students, this process it is applicable only to the preparation of aldehydes. We cannot prepare ketones as we are adding hydrogen atoms to cyanide group. Hence we can prepare only aldehydes, not ketones. Moving further, we have another alternative method for the preparation of aldehydes from cyanides, and again it is reduction process, and the catalyst used here is Dibal H. It is diisobutyl aluminium hydride. We go to the reaction. Alkyl cyanides which is treated with diisobutyl aluminium hydride followed by hydrolysis leads to the formation of aldehyde. So this Dibal H, which is going to act as a reducing agent, and expansion is here diisobutyl aluminium hydride. So here cyanides can be converted into aldehydes with the help of diisobutyl aluminum hydride followed by hydrolysis. Example, first one, we have CH3, CH, double bond CH, CH2, C triple bond N, which is treated with diisobutyl aluminum hydride followed by hydrolysis. The speciality of this reagent is which is going to react only with cyanide group, even though there is a presence of multiple bonds in the compound. So we learned in the previous slide, as cyanides can be converted into aldehydes with the help of Dibal H. So the cyanide group is converted into CHO even though there is a presence of double bond or multiple bonds in the compound. In other words, this reagent is not going to reduce double or triple bonds present in the compound. Next one, by the reduction of esters. Esters formula is RC double bond OR dash, which is again a derivative of carboxylic acid, from which OH group is replaced by OR 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 dash. R and R dash may be same or different. This ester undergoes reduction with Dibal H followed by hydrolysis. So this Dibal H is going to act as a reducing agent, which is going to break the bond between carbon and OR dash, and it adds hydrogen atoms on either side, which leads to the formation of alcohol, that is R dash OH, and aldehyde RC double bond OH. This reaction is going to take place at very low temperature, that is about 195 kelvins. Moving to the next preparation. Aldehydes can be prepared from aromatic hydrocarbons, and the product formed is aromatic aldehyde. One of the name reaction and important one, Gattermann-Koch synthesis or Gattermann-Koch reaction. So in this reaction, aromatic hydrocarbons are treated with carbon monoxide and HCl in presence of anhydrous aluminum chloride or cuprous chloride. Respective benzaldehyde is going to be formed. We learn the reaction. Benzene ring, which is treated with carbon monoxide and HCl in presence of anhydrous aluminum chloride or cuprous chloride, which gives benzaldehyde as a product. If it is a substituted benzene, we get substituted benzaldehyde, and the byproduct formed is HCl. The hydrogen atom which we get here, it is from the benzene itself. The position at which we are adding the CO group, from that position we remove the hydrogen atom. Moving to the next slide. Second one, Etard reaction. This reaction also helps to prepare benzaldehyde as a product. So here in this process, chromyl chloride oxidizes methyl group to the chromium complex, which on hydrolysis gives corresponding benzaldehyde. It indirectly means that benzene ring must contain CH3 group, which reacts with chromyl chloride, that is CrO2Cl2 in presence of carbon disulfide, which converts methyl group into chromium complex, which on hydrolysis gives benzaldehyde. In this process also we can prepare only aldehydes. Moving to the next one. The third method in the conversion of aromatic hydrocarbons into aromatic aldehydes with chromium oxide and acetic anhydride. In this process, methyl substituted benzene, which is known as toluene, or substituted toluene, is converted into benzalidene diacetate on treating with chromic oxide in acetic anhydride. The benzalidene diacetate can be hydrolyzed to corresponding benzaldehyde with aqueous acid. Moving to the reaction, we have toluene CH3, which is attached to benzene ring, which is treated with acetic anhydride in presence of chromic oxide at the temperature 273 to 283 Kelvin, which leads to the formation of an unstable intermediate called benzalidene diacetate, which on hydrolysis in presence of H3O plus leads to the formation of benzaldehyde. Moving further, the fourth method, which is going to convert the side chain into aldehyde group, that is side chain chlorination followed by hydrolysis process. So we have a side chain CS3 here. It is a toluene which is treated with chlorine in presence of sunlight, removes HCl, leads to the formation of benzyl chloride, which on hydrolysis at the temperature 373 Kelvin, as it is a hydrolysis process, water molecule is removed and that leads to the formation of benzaldehyde. Thank you, students.